In this lesson, we're going to continue our conversation about bases and vector spaces and so on. And we're actually going to find a nice way to link vector spaces to the real spaces that we are used to, the concrete ones made up of vectors and made up of spatial vectors, R2, R3, and so on. So first off, let's consider this vector. X, which is the vector 1, 6 in R2. Okay, and let's consider the standard basis. So remember the standard basis E1 and E2. These are basically just the 1 unit in the x direction, 1 unit in the y direction. And so we're going to consider the standard basis. In this, so basically we can show very quickly here that this vector x, which is 1, 6, can be written as 1 times E1 plus 6 times E2. Now, this should not come as a big surprise. If this vector space, if this basis here is a basis, that means that every vector in R2 can be written as a linear combination of E1 and E2. Certainly, if it's the standard basis, it's a fairly simple process to actually find those coefficients, to figure out how to make that linear combination. Now, one of the things we can do here is we can say that 1 and 6 are the coordinates relative to this standard basis. Okay, so rather, when we talk about linear combination, we've used the word weights for these coefficients. We're also going to, in this case, we're going to start talking about this as the coordinates. Basically a way of, well, that's it. It's just the coordinates for this, or relative to this basis. But the thing that we need to realize is this is not unique to the standard basis. It's easy for the standard basis. Figuring out those coefficients was not very difficult, but it's not unique to the standard basis. In fact, this is true no matter what basis we've got. So consider this. Let beta, or that's not beta, it's just b. So let b be this basis with all these vectors in it. And this is the basis for vector space of V. So we know that every vector in X, every vector in this vector space is the linear combination of elements of B. So we know, again, if it's a basis, then every other vector in this vector space can be written as the linear combination of these vectors. And so that means we can find these coefficients. Well, these weights, we're going to have another name for it. We're also going to call these the coordinates of X relative to this basis B, or simply the B coordinates of X. And again, it's basically a way of describing what X looks like relative to that basis. We can write these coordinates. So first of all, we have this notation. So this is just kind of our saying this is the coordinates of X relative to this basis B. And we can put those coordinates in a vector like we have here. So C1 all the way to Cn. So for example, let's consider this basis and suppose that there's some vector X such that the coordinates of X relative to this basis are -2 and 3, and we want to find X. Now let's remember that X is equal to some constant times 1, 0 plus some other constant times 1, 2. And we also need to remember that this coordinate here, these coordinates here, are those coefficients. So this coefficient is -2, this coefficient is 3. So basically X is equal to -2, 0 plus 3, 6. And so that means that the vector X we're looking at here is the vector 1, 6. So, okay, well, that looks familiar. So it's worth noting that, again, there was nothing unique about that standard basis. Again, it was easy to find those coordinates, those coefficients, but notice that even for this other basis, there are still coordinates. It's just maybe it takes a little bit more work to find them. Now, in the earlier example, I want you to note that when we found the coordinates relative to the standard basis, it was just the vector itself. Okay, so it's just useful to observe. If it's the standard basis, like I say, easy to find those coordinates, easy to find that the coefficients. Let's consider this other basis, getting a little bit more abstract, getting into the vector space P2 this time. Consider this basis. We want to find the b coordinates of this vector x, which is t plus 2 squared. And let me multiply this out here a little bit. This is t squared plus 6t plus 9, of course. But I'm going to rearrange this a little bit. I'm going to, again, think of this as some constant times my first vector in the basis 1, plus some constant times the second vector t, plus some constant times the third vector t squared. And of course, just simplifying this, we get 9 times 1 plus 6 times t plus 1 times t squared. What that tells me is this vector in B2, we can express that with coordinates. So the coordinates of x relative to this basis B would be the coordinates 9, 6, 1. Please notice the order does matter. However we list the bases in B, whatever order we list the vectors in B, we need to list the corresponding coordinates in the same order. So we want to be a little bit careful about that. So this would be the coordinates now. And again, coordinates mean just what are the coefficients? What linear combination of those elements of B result in this vector x? Okay, let's take a look at this one. Consider this basis for R2. And we want to find the b coordinates for x equals 4, 5. Okay, now one more time. What we're looking for here is we are looking for some constant times 2, 1 plus some other constant times negative 1, 1 so that the result is the vector 4, 5. Now, as I said, if this was the standard basis, piece of cake. It's not, so we have a little bit of work to do. But notice that the work we have to do is solving a system of equations. In fact, the augmented matrix would be 2, negative 1, 4, 1, 1, 5. It is worth observing that we are guaranteed that this will have a unique solution. We are 100% guaranteed it will have a unique solution because the entries in this basis are linearly independent, which means that when I make the matrix where each of those vectors is a column in the matrix, that matrix is invertible, which means that every single homogeneous equation has a unique solution. So lots of stuff that goes into this, but we just need to realize we're guaranteed that there will be one unique solution. Every vector x can be expressed uniquely as a linear combination of these vectors in the basis. Anyway, let me solve this. We can switch the top and bottom rows. Let's see. Bottom row or top row by negative 2, and then add the bottom row. So I get 0, negative 3, negative 6. Divide the bottom row by negative 3, we get this 0, 1, 2. And then if I subtract the two rows, I get 1, 0, 3, 0, 1, 2. And so I'm finding that C1 is equal to 3, C2 is equal to 2, or expressed a different way, the b coordinates of x can be written as 3, 2. There we go. Okay, so let's think about what we just did here. In the previous example, we could form the matrix P sub B, where the columns are the vectors in this basis. And that's exactly what we did. That's basically the coefficient matrix, right? That's the left side of this augmented matrix. Exactly what we did here. So we could form this matrix, P sub B, and then solving this equation, finding the coordinates are basically the same as solving the matrix equation. This is a matrix. It's a little weird because this time, this is what we're trying to solve, right? We're trying to solve those coefficients. And then x, the vector that we're trying to find the coefficients for, that's the right side, or the other side of the equation. It's a little weird. We're used to the x being the thing we're solving for, but in this case, it's the coordinates that we're solving for. It's also worth, I'm sorry, so P sub B we call the change of coordinates matrix because it's taking us from B to the standard basis. Remember I said a minute ago, the vector is itself the coordinate vector for if our basis is the standard basis. So this is basically a way of changing the coordinates from some basis B to the standard basis, right? That instead of this x, I could put x with a little epsilon there. So P sub B changes the coordinates. It's also worth mentioning, as we said a moment ago, B is a basis, which means the P sub B is invertible. So another option, if we chose to, is we could solve this equation by just multiplying both sides by the inverse of P sub B. And that's what this is right here. So that's an option if we chose to. I mean, just like, I guess that's true for any system of equation that we're solving for. We could just find the inverse and multiply instead of doing row operations. Depending on the matrix, that could be very difficult. But again, as we said earlier, the columns are independent. We've got a basis, which means that we can find the inverse. And of course, the inverse matrix maps us the other direction. It takes us from the standard basis to this other basis B, whatever that happens to be. Okay. All right, let's consider this earlier example. So in this example, we found the B coordinates of x, and we found that it was this vector 9, 6, 1. So this method of finding coordinates allows us to map an abstract vector space like P sub 2 to the more concrete vector space R cubed. So that's interesting. So right away, this idea of coordinates lets us link this vector in this abstract vector space to this vector that's in R3. I think what we're going to find is sometimes we might find it useful to, when we're talking about abstract vector spaces, we might find it useful to first take whatever vector we're looking at and convert it into its coordinates. Now, please notice in order to do that, we need to have a basis, right? We could only find those coordinates once we had first found that basis for the abstract vector space. This method of finding coordinates, I just said that. This mapping is one-to-one and onto, which means that if we've got a vector in whatever that abstract space is, not only is it guaranteed to have a vector, corresponding vector in R3, that vector is going to be unique, that meaning that it only maps to one place. Let me think for a second here. It's one-to-one, which means that this will be the only vector that maps to the vector in R3. And not only that, every single vector in R3 is going to be mapped to something from that vector space. That's the onto part. Every vector in R3 is included. This vector one-to-one onto, it is linear, so we can split it up. That makes life a little nicer. So it's a linear transformation here. Okay. Any one-to-one linear transformation from one vector space to another is called an isomorphism. Iso means the same, morph means changing, or I don't know what the formal definition, but basically just changing, shifting, altering. And the vector spaces are said to be isomorphic. So any one-to-one linear transformation is an isomorphism. What that tells me, or what this means, if two vector spaces are isomorphic, what that means is that they may look and feel completely different, but they act the same and they are indistinguishable. In other words, if I'm working with one vector space and I'm not really sure what to do, if I can find another vector space that is isomorphic, then I can do all my work in that other vector space instead, and the results can be transferred back to the first one. So we've just shown that P2 is isomorphic to R cubed. So again, that way, instead of answering questions in P2, we can instead first shift everything, find the coordinates of everything so that we're working in R3, and then answer the questions over there. And we'll see an example of that in just a moment. In general, any vector space whose basis has n elements is isomorphic to R sub n. Okay? And again, that's because if the basis has n elements, then every single vector in that vector space, we can find the coordinates with respect to that basis, and those coordinates will give us a vector in Rn. So, very, very useful. So let's consider this example. Let's show that these three vectors are linearly dependent in P2. Now, I guess we could do this algebraically, but one option here is, let's actually find the coordinates for each of these. So let me, how about we call this V1, V2, and V3. And so considering the standard, the standard basis for P2, the coordinates for V1 would be, now let's remember we have the constant on top and the x squared at the bottom. So it'd be 1, 0, 2. I'm sorry, that's supposed to be B. The coordinates for V2 under this basis would be, let's see, 4, 1, 5. It's kind of nice that the vectors are written in ascending or powers. Makes life a little bit easier. And then the coordinates for V3 under this basis would be the vector 3, 2, 0. Okay, so now to show that these are linearly dependent, we could instead show that these vectors, these vectors in R3 are linearly dependent. And remember, to do that, we could create the matrix. There are actually a bunch of different ways to do this, but we could create the matrix. And then we can perform row operations to show that this is a, basically that there's a free variable in this. So let's see here, I'll leave the top alone. Multiply the top by -2 and add the bottom, so I get 0, -3, -6. 1, 4, 3, 0, 1, 2. Multiply the middle by 3 and add them together, and I get 0, 0, 0. Okay, there is not a pivot in every column, which means that the columns are dependent. And that tells me that the vectors in P2, oops, that's an R, that's not a P. The vectors in P2 are also dependent. Okay, so rather than working with those vectors in P2, we can change them over into the corresponding vectors in R3, those coordinate vectors. All right, let's consider this problem. We've got these two vectors with V1 and V2 and this vector x. And we are interested in this basis, V1, V2. So B is a basis for H, which is the span of V1 and V2. Okay, we want to determine if X is in H, and if it is, find the B coordinates for X. So first off, I want to take just a minute. We're looking at this set of vectors, V1, V2. We're told that we're interested in the vector space, that's the span of those two vectors. I guess we're told B is the basis, but it's worth just taking a minute to verify that these vectors are not dependent on each other. Now, fortunately, it's only two vectors, so we can just look at them and say, well, no, one of them is not a multiple of the other. That's good enough. But it is worth mentioning that if I just take any two vectors and say, oh, here's a set, let's find the span of those two vectors. Those vectors don't necessarily form a basis. Remember, they have to be independent vectors. But if there's only two vectors, independence is the same as just saying that one of them is not a multiple of the other. Okay, so we want to determine if X is in H, and if it is, find the B coordinates. Yes, find the B coordinates of X. All right, so again, and we saw this before, this is the exact same idea. We're basically asking the question, is X in the span of V1 and V2? We can answer that question by setting up the augmented matrix. Here's V1, here's V2, and here's X. And let's solve this equation. And remember, we're not guaranteed that there is a solution. It is possible that this is that there is no solution here, that this is an inconsistent system, and which means X is not in the span. That's okay. But we have to check. So let's see. We got 3, -1, 3. I'm going to multiply the top equation by -2 and add the second one. We had 0, 2, 6. Multiply the... How about we multiply the top by 2 and the bottom by 3? 6 and... Wait, hold on a second. Top by 2 and the bottom by... I'm sorry, -3. Top by 2 and bottom by -3. And so this should be -5. And then top by 2 would be 6. Bottom by -3 is -21. -21 plus 6 is -15. We get 3, -1, 3. Let me divide the middle row by 2. And then I want to notice if I divide the bottom row by -5, I get the same thing. So I'll just do 0, 0, 0. And then finally, add them together. So we get 3, 0, 6, 0, 1, 3, 0, 0, 0. And I guess I'm not quite done. Let me divide the top row by 3. So we get 1, 0, 2, 0, 1, 3, 0, 0, 0. Okay. So this tells me that C1, well, let me just say this. This tells me that I guess it tells me two things. It tells me that the X coordinates, or the coordinates of X under the basis B are 2, 3. And because X has coordinates, or because this system had a solution, that tells me that X is in H. X is in the span. Okay, so therefore X is in H. Okay. All right. Let me point out just really briefly that in the previous example, H represented a plane in R3, right? In other words, a plane because it's basically just these two vectors in R3. So the two vectors define a plane. And notice that every single vector in that plane can be described by using these coordinates. In other words, every single vector in that plane could be thought of, it could be compared to a different vector in R2, and that comparison would be those coordinates. What we're basically showing is that we've just shown that this plane in R3, the subspace of R3, is actually isomorphic to R2. Because we can take any vector x that's in H. Now we know that x is part of R3, it's just also in the subspace H. Every vector H can be mapped to, every vector x can be mapped to this other vector, which are the coordinates of x in R2, or R squared, I should say. So H is isomorphic to R2. This subspace of R3 is isomorphic to R2. Cool. Okay. Next up, next thing we're going to talk about are called the dimensions, or are the dimensions of a vector space. Okay, so whoops, that's what I meant to do. Consider this. If, and this is, I got a typo here, if the basis of a vector space V has n vectors, so the basis has n vectors, then we say that n is finite dimensional, and we say that the dimension of V, written dim V, is equal to n. Basically, the dimensions of a vector space are how many vectors make up the basis. The dimensions of the zero subspace would be is just defined as 0, right? There are no vectors in there. I guess 0 is a vector space, but we're just defining it as 0. If V is not spanned by a finite set, we say that V is infinite dimensional. We'll see an example of that in a minute. And if the dimensions of V is n, then that means that V is isomorphic to n. Again, any vector in V, we can map it to the coordinates of x under that basis. But if the basis has n vectors in it, then there will be n coordinates, which means that those coordinates will be in the vector space Rn. Okay. The dimensions of P2 is 3, and we know that because when we created the basis, it was made up of these 3 vectors. P itself is infinite dimensional. Remember, P is the vector space made up of all polynomials of any degree. And so because the degree can just get higher and higher and higher, there is not a finite basis. Let's find the dimensions of this vector space. Now, actually, this is, we talked about this one just a minute ago. This is the one we used in the last example. So the dimensions of this, now again, even though we're told that the span, we're interested in the span of this, the basis has to be made up of linearly independent vectors. So to verify that the basis is that same set, to verify that this basis is made up of both of the vectors, we have to make sure that they're independent. As I mentioned earlier, because there are only 2 vectors, all that requires us to do then is to show that they're not multiples of each other, and certainly that is the case. Okay, let's look at this example. Let's find the dimensions. Oh, I'm sorry, I forgot to say. So the dimensions of H. So the dimensions of H in this case would be 2, because the basis is made up of 2 vectors. Okay, sorry, back to this one. Find the dimensions of this. So I want to point out that this is the same as the span of these vectors. So the first vector would be the coefficients for A, so that'd be 1, 5, 0, 0. The second vector would be the coefficients for B, so that'd be negative 3, 0, 1, 0. The third one would be the coefficients for C, so that would be 6, 0, negative 2, 0. And the last one would be the coefficients for D, so that would be 0, 4, negative 1, 5. Okay. Now, this, first of all, it is definitely a subspace, right? We said that any set that spans certain vectors is defined as a subspace. But that doesn't mean that all 4 vectors are required to be in that, to form a basis. It's possible that the basis has less than 3. Because these might be a dependent set. Now, it is worth noting, and we can save ourselves a little bit of grief, it's worth noting that these 2 vectors are multiples of each other. So right away, when I define the basis, I can ignore one of them because they're clearly multiples of each other. So I'm just going to ignore that one. Okay, so right away I can throw that out. So right away I know my basis has at most 3 vectors, but I still have to decide if even these 3 vectors are dependent. Maybe they're not. Or if they are independent, I should say. Maybe they're not. So to answer that question, we're going to consider the matrix made up of these columns. So 1, 5, 0, 0, negative 3, 0, 1, 0, and 0, 4, negative 1, 5. Now, it's worth mentioning, if you had not noticed that we could eliminate that first one, that's okay. Then create a matrix with all 4, okay? Certainly, if we eliminate that, it saves us a little bit of work. If I clean this up a little bit, let's see here. Top row's fine. If I multiply the top by negative 5 and add the second one, I get 0, 15, 4. And then we have 0, 1, negative 1, and then 0, 0, 5. Okay, let's keep going here. I'm going to switch the second and third rows. No, I'm not going to bother. I'll leave it the way it is. So we have 1, negative 3, 0, 0, 15, 4. Multiply the third row by negative 15 and add. We get 0. Let's see, multiply by negative 15 and add. So 0, 19, and then we have 0, 0, 5. And then finally, let's see, 1, negative 3, 0, 0, 15, 4, 0, 0, 1, and then I can just subtract to get rid of the bottom row, which is fine. But it's worth pointing out that I got a pivot in every column. If I have a pivot in every column, that means that these are a linearly independent set. And so for that reason, we can now say that the basis of this vector space is made up of all 3 of those vectors that didn't get canceled out. So 1, 5, 0, 0, negative 3, 0, 1, 0, and 0, 4, negative 1, 5. I guess I don't even need to write that because the question was simply, what is the dimension? Well, the dimension of H would be the number of pivot columns we have, right? The number of pivot columns. Because if one of the columns had not had a pivot, that means that column, that the vector that was in that column is dependent on the others, which means that, or we could also say that column would represent a free variable. And so for that reason, we would not include it in the basis. But every column that does have a pivot would be included in the basis. There are 3 pivot columns, so the dimension is 3. That's it. This problem didn't even ask us to identify the basis, although we could. Okay, how about this one? Let's find the dimension of this vector space, K, which is the span of these 3 vectors. Now, as I said before, one nice thing about coordinate setups, finding coordinates for coordinates for vectors with respect to a basis, is that it makes it easier to work with the vectors. So let me find the coordinates for each of these. So this one, the coordinates would be 2, 0, 2. This one, if I multiplied it out, it would be 1, 2, 1. And this one, the vector would be 0, 1, 0. So when I'm asking, Okay, so when I'm asking what is the dimension, again, I'm asking, are these independent or dependent? And how many of them do I need for it to actually be independent? Well, again, that's the same as asking, well, let's create the matrix with these columns. It's the same as asking the question, how many pivot columns are there? It is worth noting that if I take the top row and I subtract the bottom row just disappears. So 2, 1, 0, 0, 2, 1, 0, 0, 0. I don't have to go any further. There are 2 pivot columns here and here. And so because there are 2 pivot columns, I know that the dimensions of K, the dimensions of this vector space, is going to be 2. And because the pivot columns were the first and second, that means that my basis would be made up of just those first and second ones. Okay, so, and again, I don't need to get into it any further, but what that means is that that last vector is actually, could be written as a linear combination of the first 2. Okay, earlier we saw that a plane in R3 is isomorphic to the entire vector space R2. Let's take a look at these a little bit. So subspaces of R3. So the 0 dimensional subspace would just be the 0 subspace. Okay, so just a dot, that's the origin. A 1-dimensional subspace would be any multiples of a single vector, right? 1-dimensional means the basis is just one vector, which means that the vector space would be all multiples of that. So what we're looking at is lines that are through the origin. Now it is worth mentioning it has to go through the origin because every subspace has to include the 0 vector. So it has to include 0, the origin. A 2-dimensional subspace would be a linear combination of 2 independent vectors. So the plane, it would be then planes through the origin. We saw that earlier. And then of course any 3-dimensional subspace would be isomorphic to R3 itself, all of space. Okay, let's go back to the null space and the column space for a minute here. So notice that the dimension of the null space, remember the null space is a vector space, column space is a vector space. The dimensions of the null space of A would be the number of free variables in the equation AX equals 0. Yeah, and we saw that last class, right? Or during the last lesson, right? Where the number of free variables was the same as the number of vectors required to describe to define the null space. And so the number of free variables, basically the number of columns without a pivot, would be the dimensions of that vector space. It would be because it's the number of vectors we need to define it. The dimensions of the column space would be the number of pivot columns. And again, this basically is the same as we talked about last class. So let's find the dimensions of the null space of A and the column space of A. Please notice we are not actually asking you to find the bases. We definitely talked about that last class. But let's reduce this. I'm going to start by putting switching the first and second rows. I just kind of like having the 1 there. So 1, -2, 2, 3, -1, -3, 6, -1, 1, -7, and 2, -4, 5, 8, -4. Okay, let's see, row 1 is fine. Multiply the top by row 3, multiply the top row by 3 and add the second row, we get 0, 0, 5, 10, -10. Multiply the top row by -2 and add the bottom row, we get 0, 0, 1. See, -2, so that would be 2, -2. Okay. And then if I take the middle row and divide by 5, we get 0, 0, 1, 2, -2. which of course is the same as the bottom, so then the bottom would become all zeros. Okay. Now, I'm going to observe that there are two pivot columns. I'll label those with a P. There are two pivot columns, which means that the dimension of the column space of A would be 2, because the basis for A would be just those two, or the basis for the column space of A would be just those two columns. And then there are 3 free variables, or rather columns with no pivot. So now the dimensions of the null space of A would be 3. Okay. So some of you might be noticing an interesting observation here, just about the number of, or the dimensions of the column space, the number of the null space, the dimensions of the null space. We're actually going to come back to that very shortly. Now, in a moment here, we're going to need to talk about something called the rank. But before we do that, we need to talk about something called the row space. So we've got the column space, we've got the null space, the row space, which we're going to denote row of A. Not a big surprise there. This is the subspace that is the span of the rows of A. Right? If the column space is the span of all the columns, the row space would be the span of all the rows. So the row space of A is a subspace of R5. Please notice it's R5 because this is one of the rows, meaning this is one of the vectors defining the subspace. And this is a vector in R5. Notice, I mean, up until now we've been writing vectors vertically. Nothing wrong with writing vectors horizontally, and that's basically what we're doing. So the row space would be the span of all 4 of these rows. And because all 4 of these rows are in R5, then the row space would be a subspace of R5. As I said, there's nothing wrong with writing vectors horizontally. It is also worth observing that the row space of A becomes the column space of A transpose. I don't think that's all that useful information to observe, but notice if you just took A and wrote it transpose, all the rows of A become the columns of A transpose. And so we have this relationship. Okay. If 2 matrices, A and B, are row equivalent, so we're going to play with row spaces here a little bit. If 2 matrices A and B are row equivalent, their row spaces are exactly the same. In addition, if B is in echelon form, its non-zero rows form a basis for the row space of both A as well as B. The reason this works is because when we do row operations, we're resulting in B, right? Basically, B is the end of that process. B is the echelon form where we're, after we've done the row operations. When we're doing the row operations to come up with B, the result is just a linear combination of the rows of A. And, well, if you take a basis and create some linear combinations, you're just basically creating a new basis. So this is kind of useful, right? If we're looking for, in fact, here, let's play with this. Let's find the bases for the row space of A, the column space of A, and the null space of A. And here's A, is this vector here. Well, let's play around with it. Let's, to answer any of these questions, we need to find the echelon form. So I'm going to switch the top and bottom, or the first and second rows. Again, I kind of like that, having that 1 there. So 1, 3, -5, 1, 5, -2, -5, 8, 0, -17, 3, 11, -19, 7, 1, 1, 7, -13, 5, -3. Okay. Top row's fine. Multiply the top row by 2 and add the second row. I get 0, 1, -2 to -7. Multiply the top row by -3 and add. We get 0, 2, -3 is 15, so -4. -2, or wait, -3 times that would be 4. -3 times would be -14. And then let's just do row 4 minus row 1 would give me 0, 4, -8, 4, -8. That's interesting. Okay. Top row is fine. I don't know why I'm squishing these. Oh, I know, because I need more space. We got 1, 3, -5, 1, 5. 0, 1, -2, 2, -7. Okay. Second row times -2 plus the third row. So 0, 0, 0, 0. Oh, 0. Okay, fine. You guys are probably watching the video saying, why did he stall? The answer is because I was kind of surprised it worked out that nicely. That's okay. Second row times -4 plus the bottom row gives me 0, 0, 0, -4, and then 20. Okay. And I guess I can clean this up just a little more. Oh, actually, I do need to keep going. I need this in a reduced echelon form. So this will be 1, 3, -5, 1, 5, 0, 1, -2, 2, -7. Let me switch them to reduce. We get 0, 0, 0, 1, -5, and of course 0, 0, 0, 0, 0. Okay. But yeah, I do need a reduced echelon here. So bottom row's good. Second or third row's good. Multiply the bottom row by -2 and add the third row. We get 0, 0, or no, I'm sorry, 0, 1. 0, 1, -2, 0, 3. And if I do top row minus the third row, I get 1, 3, -5, 0, 10. Okay, and I think I'm almost done here. 0, 1, -2, 0, 3. 0, 0, 0, 1, -5, 0, 0, 0, 0, 0. Okay. And then if I do the third row times -3 plus the top row, I get 1, 0, 1, 0, 1. Okay, apparently I speak binary. That's cool. Okay, so this tells me that x1 is equal to -x3 minus x5. This tells me that x2 is equal to -2x3 minus 3x5. I'm sorry, that should be positive. I get a plus. Positive 2x3 minus 3x5. And x4 is equal to 5x5. And so my solution is, well, all my, let's see here. So -1, 2, 1, 0, 0 times x3 plus -1, -3, 0. Oh, I messed up that last one. Hold on. Let me try that again. -1, 2, 1. Oh, I guess it was 0, 0. That's okay. I guess I had that right. Okay, and then -1, -3, 0, 5, 1 times x5. Yeah, just remember this is a 1 here because x3 is equal to x3. And this is a 1 here because x5 is equal to x5. Okay, so we need bases for all these things. So first of all, the basis for the null of A, so the null of A is going to be the span of these two vectors that I just found. Be -1, 2, 1, 0, 0, and -1, -3, 0, 5, 1. Okay. The column space of A is going to be the span of, now we need to remember the pivot columns were columns 1, 2, and 4, but we need to remember that we have to take from the original column, so 1, 2, and 4. So it's going to be the span of those three vectors, -2, 1, 3, 1, -5, 3, 11, 7, and 0, 1, 7, 5. Please remember that the pivot columns tell me which columns to choose, but I need to go back to the original columns. And then finally, for the row space of A, we've just identified that we've just said all we need to do is worry about the rows that are pivot rows, but we can go with the reduced echelon form, or even just the echelon form itself. So those rows, those vectors are, and I'll just write them horizontally because we can. Those vectors are 1, 0, 1, 0, 1, 0, 1, -2, 0, 3, and 0, 0, 0, 1, -5. And it really doesn't matter if you write them horizontally or vertically. Who cares? I mean, I could have written those vertically and it would have been the same thing. Okay, so there's our bases for these three vector spaces. Now, some observations we can make here. First observation is that the basis for the column space of A uses entries from A, but notice that the bases for the null space and the row space had no connections to the entries of A. Again, when I found the column space, I had to go back to the original matrix. But the null space and the column space, we had to work with the reduced forms. Also, one other really quick observation. I could have, if I was looking for nothing more than the row space, I could have stopped right here. Actually, maybe even stopped right here, I guess. But I could have stopped right here because as soon as I know which rows are my pivot rows, that's good enough, right? I could use these three rows and that they would also form a basis for the row space. But to find the null space, I had to keep going all the way. So that's why I did that. Okay, it's also worth observing, although the first three rows of the echelon form are independent, you can't assume the same is true of A. Okay, in other words, back to this again. When we found echelon form, the first three rows are independent. Okay, and that's great, that's perfect. But notice that these three rows came after we rearranged some of the rows. Here, right, we switched rows 1 and 2. Over here, we switched rows 3 and 4. So even though the first three rows of the echelon form are independent, we don't know that the first three rows of the original matrix are independent. In fact, we know one of the rows will be dependent on the others because one of the rows has all zeros. So it might be one of those first three rows that is dependent on the other two. In which case, so my point is simply this. when it comes to finding the row space, we need to use the rows from the echelon form or the reduced echelon form. We can't, like with column space, we can't just say, oh, pick those rows. Okay, now go back to the beginning and pick the rows from the original matrix. Because, yeah, we made some changes along the way. Okay, now we need a definition here. The rank of a matrix is the dimension of the column space of A. Okay, that's our definition. The rank of a matrix is the dimension of the column space of A. And we have a theorem here. The row space and the column space have the same dimensions. Okay, that kind of makes sense, right? Because wasn't the dimensions of the column space how many pivot columns there were? Well, the dimensions of the row space are how many pivot rows there are. And I mean, both of those, the answer to both of those questions is how many pivot positions there are. So these are going to have the same dimensions. If A is an m by n matrix, the rank of A plus the dimensions of the null space of A is equal to n. Think about that for a second. And here, oh, why are these true? Okay, we're already answering that. If A is an m by n matrix, so that's the number of rows by the number of columns. So there are m rows and there are n columns. The rank of A would represent the number of pivot columns, right? Because it's the dimensions of the column space. We look for pivot columns. And the dimensions of the null space would be the number of free columns. And well, every column is either a free column or a pivot column. So if you add those together, you're going to get the total number of columns, which would be n. Okay, so this kind of makes sense. And of course, this can also make our, be pretty useful to our work. So consider this. If A is a 7 by 9, if A is 7 by 9 with a two-dimensional null space, what is the rank of A? Well, this is 7 by 9, so there are 9 columns. Of those 9 columns, 2 of them are free, which means that 7 of them are going to be pivots. And if there are 7 pivot columns, that means that the rank of A is equal to 7. That's it. I mean, that's the whole point. That's the whole idea here. They add up to that. Now, could a 6 by 9 matrix have a two-dimensional null space? If we went through that same process, that same thought process, the two-dimensional null space would lead me to believe that, again, there are 7 pivots. But think about that for a second. This is a 6 by 9 matrix. There are 9 columns. There are only 6 rows. There is no way to get 7 pivots with only 6 rows. So the answer for this case would be no, it's not possible. Of course, if this was any number bigger than 7, right? We already saw it works for 7. If this number was any number bigger than 7, it would also work. Okay, sure, we can have 7 pivots even though there are 12 rows. Who cares? All right, consider this problem. Suppose a homogeneous system of equations with 18 equations and 20 variables is found to have a two-dimensional set of solutions. Oh, sorry, that should be is found to have a two-dimensional set of solutions. Does every associated non-homogeneous set have a solution? Well, let's see here. So it's a homogeneous system of equations, 18 equations. So that means that our matrix has 18 rows and there are 20 variables. So there's 20 columns. Now, once again, we're told that there's a two-dimensional set of solutions. And remember, we're setting this so times x equals the 0 vector, right? Because this is a homogeneous system. What that tells me is that x is equal to two-dimensional set of solutions. That means that x can be written as some vector times one parameter plus some other vector times another parameter. And if that's the case, that tells me that the null space, the dimension of the null space, is equal to 2. Right? When we found the basis of the null space earlier, that's what we found. And of course, if that's true, then the rank of A is equal to 18, right? 20 minus 2 gives me that 18. But if the rank of A is 18, if there are 18 pivot columns, but there are also 18 rows, that means that every row will have a pivot. Every single row of this coefficient matrix has a pivot, which means that every single homogeneous system will have a unique solution. If instead of a 0 here, if this was some other vector b, we're guaranteed that there's going to be a unique solution. Basically, we're guaranteed that the system is consistent because every column and every row has a, I'm sorry, not every column has a solution. Yeah, let me back up for a second. The non-homogeneous solutions will not be unique. They're not going to be unique at all because there's this, I'm sorry, I misspoke, because there's these parameters. But every solution, every system will be consistent because every single row has a pivot. There's no way, if I put a vector over here, there's no way for the pivot to be right here because every row already has the pivot. Sorry if that was a little confusing. I got lost there a little bit. Okay, one more thing to talk about, and that is back to that invertible matrix theorem. We have all these different conditions for an invertible matrix. Please remember, this only applies to square matrices. And to that, we can add some other things. First of all, the column space of A is all real numbers. Basically, we said that the invertible matrix will have a pivot in every row and a pivot in every column. What that means is that well, actually, this goes back even more, doesn't it? The columns span all of Rn, which means that the column space is itself Rn. The row space is also all of Rn because do I have it here? Maybe I didn't write it. The rows are linearly independent. You know what we could say? This would be true because, how about we go this route? This would be true because the row space of A would be the column space of A transpose. And I don't think I wrote it here, but one of the other equivalent statements is that if A is invertible, then A transpose is also invertible. Yeah, okay, so that takes care of the row space. And then the null space is the 0 subspace. Well, let's think about this. If every single, let's see, A has n pivot positions. Every single row and every single column has a pivot position, which means there are no free columns, which means that the null space is going to be made up of no vectors. It's just the 0 subspace. Okay. We covered a lot of ground here talking about these subspaces and so on. That is the end of this lesson. Thank you very much for viewing.